It's lovely to be here. It's great to see friends that, well, maybe we haven't gotten together for a while. It's great to see so many new people coming to this event. It's a really fantastic gathering of the entire quantum ecosystem. Now, I do appreciate that there is a huge diversity of audience members. Some of you are PhD students and researchers. Some of you are representatives of government. Some of you are potential end users of quantum technology. And what I want to do with this talk is try and thread a very difficult needle and give a little bit of something to everybody. So I want you to be able to come away from this talk understanding how this new thing, quantum infrastructure software, is really accelerating the pace of turning quantum technologies into useful capabilities. And I want to show for the experts in the room some really exciting new results that redefine the state of the art in both quantum computing execution on real devices and in quantum sensing. So my name is Mike. I'm the CEO of Q-CTRL, and we build AI-powered infrastructure software. If you've not heard of infrastructure software before, this is the technology that connects low levels in the so-called computing stack, things like the actual hardware, to the high levels of abstraction. The algorithms, the developer tools, the programming frameworks that everybody tends to talk about. In the middle, we have the glue. And the glue is what makes it actually work on real devices. Our primary focus, as you would understand, based on what is the challenge in the field, is on performance management, trying to make quantum hardware perform better by dealing with the problem of error. I am, for the AV team, going to assume that the clock not starting means I can keep talking. If you're not familiar with Q-CTRL, we've been around for now 6.5 years, and we've demonstrated a track record of being really one of the only companies that validates our tools on real hardware consistently, that builds and releases products to the public for anybody to use. We don't talk about pre-release things, we release things. And we're very excited that we've really pushed the limits on what is possible with quantum devices. We're now, in quite an exciting but also terrifying way, up to almost 120 staff members in the United States, Los Angeles, in Sydney, in now Oxford, and in Berlin. And we were very pleased, although these are silly vanity metrics, to raise the world's largest Series B in the world, the world's largest in the world, from Australia, in the world, for quantum software. We so often shrink in Australia and say, well, maybe we can do something good for Australia. F that, we can do things that set world records. When we think about who we're working with, we have, at this time, we just crossed 16,000 individual software users. It's difficult to keep these slides up to date. We service end users in governments, in national laboratories and the like. We work with commercial partners, teams that build quantum computers and teams that use quantum computers. We're very pleased with the partnerships we have all around the world, including with our local partners at Iraq, and we're happy to extend a very warm congratulations to them for opening their R&D facility yesterday. And also, of course, working with teams in academia all around the world. The motivation for all of this is, I think, something that everybody can get behind, that there's a lot of excitement around what the opportunity is, the technological, the strategic opportunity, and of course, the economic opportunity linked to the development of quantum technologies. And this is what the Boston Consulting Group has said so many times, is over an $850 billion market opportunity because it touches everything. It touches transport and logistics, pharmaceuticals, new forms of machine learning, defense technology. Everything has the potential to be impacted. This is driving so much private sector and public sector investment. And it motivates a lot of the talks we've heard so far, including the talk before lunch about making these beautiful developer tools to make it easier to code quantum algorithms. Anybody who's actually tried to run something on a quantum computer would then be familiar with what makes it so hard. That is the idea that errors in the hardware tend to obscure the results that you want. Now, this is totally different than the way we operate regular computers. You can run your computer, your laptop, for literally 1 billion years and never suffer a hardware error. And in quantum computers, we all know that this more like 1,000th of a second as an average across the community before things go south. In this example, running something called Grover's search needle in a haystack type problem, when you try and find that answer, that location of the needle in the haystack, and you run it on real hardware, that's real data on the bottom, you just get random nonsense out. And so a huge amount of effort goes into trying to address this problem. We see all around the world that there are teams of academics, teams in national labs, teams in industrial settings who are building and deploying countermeasures to effectively reduce these errors through various techniques. These are things like quantum error suppression and error correction and error mitigation. If you as a user want to get useful results out of a quantum computer, first of all, you have to know what every one of those things is. You have to know how to put them together. You have to know how to configure them to actually work. It can be many tens of thousands of lines of code to put together the appropriate, say, Qiskit program that actually will give you a useful result. And it tends to incur a huge amount of overhead. You have to run and post-process and the like. This has been the domain of experts. It's people like our team, it's people in academia who have focused on these efforts. And it's led to this huge gaping chasm between the skill sets that are held by people in enterprise, end users in defense, and the actual strategic advantage that they're trying to gain. Again, the Boston Consulting Group says 90% of value capture will go to early adopters. But this makes it really hard, getting useful results. And our view at Q-Control is it just doesn't have to be this way. So in December, we were very pleased to announce that our performance management infrastructure software was running natively, fully configured within IBM Quantum Services. In addition, available through our own cloud service called FireOpal. What that means is that everything that needs to be done to get useful performance out of real quantum hardware is reduced to one setting. It's a setting you must set. You must set a channel strategy when you're working with Qiskit, and all you have to do is set that the channel strategy is Q-Control. Once you do that, everything else is completely automated and invisible. Now, for the experts in the room, there's actually an enormous amount of work that goes on behind the scenes, building a completely autonomous zero-config workflow. Again, for the experts, it involves a very rapid compilation step. It involves layout selection via our own learning-to-rank machine learning algorithm. It involves eliminating crosstalk in the circuit via our own autonomous, optimized, contextual dynamic decoupling. It involves a complete AI-driven process to redefine the entire machine learning on the chip, and it involves managed hardware execution. All of that is done for you. There is not a single setting. There is nothing that you have to do aside from selecting the channel strategy. And what it delivers is really quite profound. You see not tens of percent or factors of 2, but orders of magnitude improvement in the performance according to a wide range of metrics. Over 1,000 times more likely to get the correct answer out of benchmarking algorithms like Bernstein-Vazirani. You can get the correct answer with more than 99.9% confidence, validated, again for the experts, by bootstrapping experiments, in algorithms like Bernstein-Vazirani or QFT with less than 1,000 shots, less than 1,000 executions. The numbers start to blow out when we talk about more complex algorithms to hundreds of thousands of times performance enhancement, and all of these protocols run on systems with over 100 qubits. 127 qubits are the largest devices from IBM. I do want to emphasize you do not need to take my word for it from this slide. This is published in the peer-reviewed literature in PhysRev Applied from our team. It's published by the QEDC independently, and you can just use it and compare against our online documentation. Get the results yourself. So with all of this, we were pleased to have a bit of fanfare when we announced this in New York at the IBM Quantum Summit. We had a congratulatory message from NASDAQ and a giant billboard in Times Square, which I would say is the peak of my career journey in Q-Control. But back to the reality here. We're very excited about applications of quantum computing in a new class of algorithms that are focused on optimization, scheduling, and routing. And many of you know we've talked about this before based on partnerships we have with, for instance, the Australian Army, where we recently did a demonstration of how quantum computing could be applied to a major logistics challenge that they face. And we showed that quantum solutions could actually give superior answers to high-quality commercial solutions. Now, this was at tiny scale. It's demonstrator only. We are not claiming any kind of quantum advantage. But you could actually get really useful insights. And it showed a pathway towards larger scale implementation. I want to drill down on one kind of problem in this general direction. And that is known as max cut. This is a machine learning type problem that involves what's called a graph. So a graph visually is just this connected series of dots. And what we want to do in this problem is bisect that graph into two separate pieces, two subgraphs they're called, in such a way that we maximize the number of connecting edges that we cut. It's called max cut. And that problem is relevant to all sorts of things in machine learning, in finance, in circuit diagnostics, and the like. It's the math problem that you care about for other applications. Now, what you can see is that when the problem is pretty small, it's reasonably easy to visually identify the correct maximum cut. But as the problem gets big, as there are many, many nodes, it very rapidly gets hard. So this is a problem that has been mooted as one amenable to quantum computing. And the way people think about this is via an algorithm called QAOA, Quantum Approximate Optimization Algorithm. It's a hybrid algorithm that involves a little bit of quantum and a lot of classical compute around it. It's great because since it involves a little bit of quantum, it fits on the machines that we have today. It's less great because it's hard to get proofs that it gives very substantial advantages, and it's actually very, very hard to implement on hardware. There are lots of SDKs and toolkits that start from the top down and say, here's how you run QAOA. And the sad reality is that they just broadly don't work on hardware. There's a huge amount of configuration that has to be done in every part of the QAOA execution. Now, what we have done is we've packaged this all together, solving everything from the way you execute the circuits with error suppression through to the classical optimization that goes on around it. As a first step, we were benchmarking against published literature from JP Morgan, looking at max cut on an alternate hardware vendor versus max cut that we would execute with our tools on IBM. And what we were able to show is that at this, in this regime of 30 to 40 qubits, where you start to get failures in the alternate vendor, so yellow means sometimes it works and red means they never get the right answer, we ran exactly the same problem instances, and every time we get the correct answer. And I want to emphasize something very much for the technical members of the audience. This is full hybrid execution on hardware. There is no classical pre-compilation. There is no classical simulation involved. You do everything on the device. And it's 30% faster to do everything on the device than to run one pre-compiled circuit on the alternate. Now, another way to visualize this, and something we were very proud of, is by looking at the outputs of the algorithm. Now, the output is some distribution of possible answers, and you want your distribution to overlap with the best answer, the maximum cut. What we showed in December was this amazing result where we could actually demonstrate the quite substantial QAOA advantage, shifting that distribution towards the maximum cut, actually overlapping with and finding the maximum cut in a way that was many orders of magnitude better than you could do with a brute force sampling. Now, I'll emphasize these are non-trivial graphs. They are three-regular. They are not matched to the topology of the device. There's all these characteristics that make them hard classical problems. And yet we're running it here. Now, I want to point out also, if anybody was at the QIP rump session or saw it, you know, there was a huge amount of joking about how QAOA is no different than random sampling, than brute force. Well, that's what the red graph is, which broadly is without Q-control. But if you turn Q-control on, you get this benefit. Now, we were quite pleased with this. It was a great result. But of course, that was all the way back in December of 2023, and it's, what, February 20th now. So in the intervening time, we have set totally new records by doing full hybrid execution with 100 qubits on the same category of problems, 100% on the device. Every single instance we've run, we have found the maximum cut. And you can see that now these distributions are dramatically separated, which is indicative not only of the role of error suppression, but also all of the other tricks that we have done to get the best possible performance. This is, as best we understand, plus some demonstrations we've done on spin glass type problems, the biggest full hybrid execution that uses all of the devices on the chip. So going back here, what we're able to do, because we started at the bottom, we started at how you make the hardware perform better, is start to build upwards. All of these tricks we've done to get the results I showed you in a minute ago, they can now be abstracted and turned into a black box. So you as a user are actually now facing an opportunity to never worry about a quantum circuit. You don't have to think about what is the hard mixer you choose and all these things. You just, in FireOpal, say solve.qaoa. That's the entire command, and everything else is orchestrated for you. It is available right now in that product. So somebody had to use a lame Harbor Bridge analogy here, and I took that on myself. The objective is to bridge the gap between those skill sets that people have today and what people actually want, which is the useful outcomes from quantum computers. And we're very pleased to be contributing in that way, starting with performance management and building new capabilities upwards. This is what Heather West at IDC calls frictionless quantum software, supporting a broader range of users getting into this field. So she says, quantum software vendors like Q-CTRL help to ease the IT developers' learning curve so enterprises can leverage current IT skills. This is something where I think it's very important that we start to branch out and think about what our customers need instead of what's most scientifically exciting to us, and that's something that we've focused on quite substantially. That's where we are with quantum computing, but from the day that we started the company, we have never been just a quantum computing company. We are a quantum technology company, because we knew that parallel verticals could also benefit from this technology. In quantum sensing, which we've heard a lot about, there is this huge opportunity to deliver really substantial advantages in sensitivity, in stability, how the signal changes or doesn't change over time. But in practice, these devices tend to be relegated to the laboratory. That's because when you take them out, all sorts of sources of interference cause degradation in performance, just like we see errors causing hardware failure in quantum computing. Our approach to this is to again leverage infrastructure software to solve these problems. We were extraordinarily excited that in July of last year, we were able to announce our partnership with the Australian Department of Defence in relation to the AUKUS trilateral partnership, bringing this new category of software ruggedized quantum sensors to key problems in navigation. And the Times wrote this feature article about us. Navigation is one of three key areas that we focus on. How do we leverage quantum sensors to enable us to navigate when there is no GPS? You heard a lot about that yesterday if you were around. So we have built the world's smallest mobile 3-axis quantum inertial measurement unit. There is nothing like it in the world. The sensor itself is the size of a basketball. It operates on moving platforms by leveraging software to combat the problems that happen when you put it on a boat or an aircraft. We announced a partnership just recently with the United States Geological Survey, focused on how quantum-enhanced gravimetry, very similar technology as accelerometry, gravity is just a kind of acceleration, can be used not only for minerals, but for underground target detection, for water monitoring, and the like, but also that device can be used for navigation. That's actually a portable dual gravimeter gravity gradiometer for the experts in the room. And last, focusing on intelligence, surveillance, and reconnaissance with the Army via quantum magnetometry. This allows all sorts of exciting developments in anti-drone warfare, but also in furtive communications and the like. But remember, in every case, our focus is on how this hardware which we build can be augmented with software, software-enabled, software ruggedized. So we put a lot of effort into how all of the technology we developed for quantum computing could be ported over to this domain. And last year, we published a manuscript in Nature Communications which showed for the first time that you really could get very big wins from this perspective. So what we did is pretty simple. We took an atom interferometer, for those of you who know. We used it to measure inertial accelerations. We then took that atom interferometer and we shook the shit out of it until the signal went away. So effectively, those wiggly lines, that is the signal. That's what we want. That's how we derive an indication of the acceleration that's being experienced by the device. And we shake it harder and harder and harder until it just blurs out and there's no signal. And then all we do is effectively, figuratively, flip a switch and turn on our software, and the signal comes back. So the difference between the black and the purple is the difference between how these devices are typically run by everybody else in the community, and then how we run it with our software ruggedization. And this demonstrates more than 20x enhanced environmental tolerance. So how badly can the device be shaken and maintain the same performance, increased by more than an order of magnitude with this kind of technology. So I've told you about how we're using infrastructure software, the software in the middle, to actually make hardware perform useful tasks. And I've shown you how we can leverage this to open new regimes in what is possible, what IBM calls the utility scale for quantum computing, and how we've used this to really advance the state of the art in quantum sensing. So, if you would like to learn more about how to access this technology, if you're a manufacturer and you want this technology natively on your hardware, we have 2 more partnerships that we'll be announcing later in the year in that direction. Or if you just like to learn more about quantum software and the application in quantum sensing, please feel free to get in touch. And with that, I'll thank you very much for your attention.